In this video, we'll cover Breusch-Pagan Test, a statistical tool for detecting heteroskedasticity in regression models. We'll compare two simple OLS regressions, one homoskedastic and one heteroskedastic. From each regression we collect fitted values and residuals, labeled homofit and homoresid, and heterofit and heteroresid. Our goal is to apply the Breusch-Pagan test to those residuals and decide whether heteroskedasticity is present. In Mathematica we've loaded 200 observations for both sets of fitted values and residuals, plus the 200 values of the independent variable x, which are shared by both regressions. This is the scatter of residuals and fitted values from the simple OLS regression with heteroskedasticity in the dependent variable. Notice how the variance, or spread, of residuals increases as we move from left to right, along with the fitted values. Here we plot the squared residuals against the same horizontal axis, the fitted values. Observe the clear quadratic pattern in the scatter, following the fitted quadratic curve. This pattern indicates heteroskedasticity. Now, take a look at the scatter of residuals and fitted values from a simple OLS regression with homoskedasticity in the dependent variable. Notice that the variance, or spread of residuals, remains roughly constant as we move to the right. Again, here we have squared residuals plotted against fitted values. There's no obvious quadratic pattern, the fitted curve is nearly horizontal. This shows that the data are homoskedastic. This overlay graph combines both residual plots. Notice the red points showing heteroskedasticity and the blue points showing homoskedasticity. Finally, in the overlay of squared residuals, the red pattern clearly reflects heteroskedasticity, while the blue homoskedastic data lie almost flat along the horizontal axis. Let's apply the Breusch-Pagan test to check for heteroskedasticity in the residuals named heteroresid. To run the auxiliary regression, we define the dependent variable y vector as the square of heteroresid. Next, we create the X matrix with two columns, the first column of ones for the intercept, and the second column of X values.
Now, we input the matrix formula to estimate the beta vector. We'll need the coefficient of determination from this auxiliary regression to compute the Breusch-Pagan test statistic. So, we calculate the residual sum of squares and the total sum of squares. From these, we obtain r squared. And then the test statistic, n times r squared, where n is the number of observations, 200. The computed test statistic is 33.26. The null hypothesis of the Breusch-Pagan test states that the residuals, heteroresid, have constant variance. We'll now check whether to reject this hypothesis. We define the chi-square distribution with 1 degree of freedom, since there's one explanatory variable. Observe the graph of this distribution carefully. Our calculated test statistic lies in the right tail. The area under the curve to the right of this point represents the p-value, which is almost zero. This is confirmed by the Mathematica output. Hence, we reject the null hypothesis and conclude that hetero-resid exhibits heteroskedasticity. Now, let's turn to the residuals named homoresid, and apply the Breusch-Pagan test to check for homoskedasticity.
To run this auxiliary regression, we define a new dependent variable, y vector, as the square of homoresid. The X matrix remains the same as before. Next, we input the matrix formula to estimate the new beta vector. We then compute the residual sum of squares and the total sum of squares to obtain the corresponding r squared. And finally, the test statistic, n times r squared. This time, the computed test statistic is 0.175. According to the Breusch-Pagan test, the null hypothesis states that the residuals, homoresid, have constant variance. We'll now determine whether to reject this hypothesis. Look at the graph of the chi-square distribution. Our calculated test statistic lies well within the left portion of the curve. The area under the curve to the right of this point represents the p-value, which Mathematica calculates as 0.676. Since 0.676 is quite high, it indicates a large probability of committing a statistical error if we reject the null hypothesis. Therefore, we safely conclude that homoresid exhibits homoskedasticity.